Alright, this problem is the exercise in the lab that you did on Tuesday, where we had a cart on a horizontal ramp being pulled by a string. At the other end of the string was a hanging mass, and the force that made all this move was the weight of the hanging mass. So what we want to do is, with this problem, look at it from two different vantage points and make sure that they give us the same answers. The first vantage point is we'll call our system both the cart and the hanging mass. Okay, and so really, what is the force that acts on that system? Well, the force that's making this whole system go is just the weight of the hanging mass, which equals mhg. Okay, what does that force move? What accelerates because of that force? Well, certainly the hanging mass accelerates. So that's part of it. But also because the string is connected to the cart, internal to our system, then the force due to the weight of the hanging mass also accelerates the cart. Okay? So I have an expression for the force, I have an expression for the mass. A equals F over m, that's Newton's second law. So in this case, the force is mh times g, and the mass is mh plus mc. Okay, so this was a very easily derived expression for the acceleration of that system when we consider it as the two masses in the string together. So this is simple. Hopefully it's commonsensical, and what it means is that I can quickly come to an idea of what the whole system does. But it does not help me know what goes on in the system. For example, I don't know the tension in the rope. Okay? So, let's look at this same exact problem from a different vantage point, where I'll break it into two systems. The first system is the hanging mass. It has weight down, and it has tension up. If it's not moving at all, those are equal and opposites, and the weight stands still. But if it is moving, then I can use Newton's second law to describe that motion. Now, what we're going to do is we're going to say direction-wise that to the right is positive, and if that's positive in that direction, then downward is positive as well. We're really thinking of the pulley here as just a way to turn the middle of the system, not as like two different accelerations, because these are all tied together. So in this case, if I do Newton's second law, for the hanging mass, then I have my weight downwards, mhg is my weight downwards, and I have my tension upwards. Sorry, I got my sign wrong here. I got my tension upwards, and that equals MHA. Okay? So this equation is an expression for what's going on to the hanging mass alone as it accelerates. Now, what if I look at a free body diagram for the cart? I have its weight, and it doesn't go anywhere vertically and horizontally, so I have the normal force. Those are equal and opposite and cancel. But I also have a tension that pulls this mass to the right and accelerates it. So my Newton's second law equation here is my tension equals MCA. Okay? So that's, again, fairly simple. The cart moves because the tension pulls it to the right. That's what Newton's second law for the cart says. The weight moves downward. It doesn't fall free fall. If it did, mhg, its weight, would be the only thing working on it. But tension is pulling it upwards, so it's the difference between the weight and the tension that makes the cart accelerate. So hopefully that makes some sense. Now, In this situation, I don't know A, but I have a really nice expression for A from before. So if I look at that, I can substitute that in here. I get MC MH over MC plus MH times G. Okay? And what we find, if you evaluate this expression here, is that the tension in the wire is actually less than MHG. So MHG is just the weight that causes this whole thing to move. But the tension in the wire is actually going to be less than the weight. It has to be less, otherwise it wouldn't move. This tension here is the same as this tension here. I'm sorry, I don't know why I called it T3. Let me get rid of that. So these tensions are the same. If the tension here was the same as the weight, then the hanging mass wouldn't move. So what we conclude is this is an expression for the tension of the rope, and it will be less than MHG. Now in class, I also derived an expression for the tension by looking at this without using the previous problem. So how would I combine this equation and this equation to come up with the same equation here? Can I look at this as two different systems and come up with the same equation? So this is where the algebra got messy in class, and I kind of goofed things up. What we know though is that the acceleration is the same for both. If I look at it just from the point of view of the cart, tension divided by the mass of the cart is equal to its acceleration. Okay, that's what that equation says. If I look at it from the point of view of the hanging mass, then the weight minus the tension divided by the hanging mass is its acceleration. So now if I set these two equations equal and I solve that, getting rid of this, I should be able to find an expression for T, and that expression should be the same as what I found before. So let's multiply both sides of this equation by MH. Let's add T to both sides. And let's take T out. Okay, and then let's divide by this fraction that's in the parentheses. Okay, now this thing on the bottom does not look, I can represent it in a different way. What I'll do is I'll internally change this 1, I'll change that to MC over MC. Okay, same thing, and then I can flip this fraction and I get T equals MC MH over MC plus MH all times G. And that, if we look, is exactly the same as our equation that we got using the previous effort. So no matter how I look at the system, as one system pulled by the weight, or as two different systems that are connected by a string, I get consistent results for acceleration and for tension.